We can determine the capacitance of other uh, configurations basically the same way as we did with the parallel plates. The first thing we need to do is find the electric field in between the two conductors and then integrate along the path of the electric field. In this case, we have a coaxial cable. Many of you are probably familiar with this with your televisions. You have a center conductor that's wrapped around concentrically with an outer conductor, and there's air inside, or it could be some kind of material inside. So we need to first come up with the electric field. The electric field we found in chapters 21 and 22 is equal to lambda over 2 pi epsilon naught times r, r being the distance away from the conductor. Now, lambda was defined as the charge divided by the length. So we can substitute that into our electric field equation. We get Q over 2 pi epsilon naught L times R. And now we're ready to do our integral. So we have V is equal to the negative of the integral of the electric field dot dl. And we can put in our information here. So that's going to be from RB to RA for our limits. Put in our electric field. And our dl is just going to be a differential distance in the r direction. And we can take the constants out. And we're left with an integral from RB to RA of dr over r. And dr over r is just the logarithmic function . And now I can take and put my limits in. And remember that when you subtract two logarithms, it's the same thing as dividing. So we can use the logarithmic relationship. So we got the natural log of RA over RB. And if I want to get rid of this negative sign, I can do that by flipping the ratio inside the natural log, and that gives me Q over 2 pi epsilon naught length natural log of RB over RA. Now, we can find the capacitance is equal to Q over V, and that's equal to Q over Q divided by 2 pi epsilon naught L natural log RB over RA. And we can simplify this, and I'm going to leave the natural log in the denominator. The q's are going to cancel out. The 2 pi epsilon naught L is going to be taken to the top, and I'll divide that by the natural log RB over RA. Now the interesting thing about this formula is that we can adjust the capacitance. If I get coaxial cable with an inside conductor radius of RB and an outside conductor radius of RA, and I can't change those, but I can change the length. So the capacitance can be changed by cutting the coax to a specific size or specific length. So the longer the length, the greater the capacitance. So this is a unique feature of a coaxial cable that makes it very useful in radios and radio transmitters, especially high power radio transmitters. This idea of being able to change the capacitance by changing the length of a coax is a very nice feature that you can use to your benefit.